Hello, everyone. I'm glad to be back today. I hope you guys can hear me well. Um, so as usual, there is the chat, but apparently there are some Zoom updates, so sometimes not working. But I can see Elaine Lajoie. Hello, it's nice you can write on the chat. Perfect. And you can also find the Q&A button. So today I will present you a short presentation on on Hawking radiation, and we'll have maybe 30 minutes presentation and 30 minutes questions. Um, we're gonna wait like a couple of minutes before starting so that everyone can arrive. Um, hello, hello Steven, hello Zed, hello Pavel. Um, I'm glad to see that there are many of you tonight. A lot of people also from Canada, from the US, people from France and Europe, Czech Republic, nice, and from Brazil, wonderful. So tonight, yeah, I hope it won't be too difficult. I will try to make it as layman as possible, and uh, and the idea is really to focus on one specific point of our research so that you can understand, and it's a very fundamental one. And I hope it will bring new insight for you to understand how our universe works. So I'm gonna start soon the presentation such that, and then throughout the throughout the presentation, you can leave your questions, and we'll try to address them. I will invite also the people who wants to ask their questions to speak live, so that we can interact. Um, so I'm gonna start to share the screen. Let's just start present like that. So yes, so maybe you can start. So as I said, tonight we're gonna talk about Hawking radiation, and more specifically how the ground state level of any field, and especially the electromagnetic field, um, is determined by the gravitational field of, uh, of the local gravitational field. Uh, just to give you a little bit of context. So first thing, we put the last version of the what it used to be called the origin of mass paper, but we made like so many improvement of it, and now we called it extending Einstein-Rosen geometric vision, vacuum fluctuation induced curvature as a source of mass, gravity, and nuclear confinement, that you can find online very easily, either on the website or on the preprint.org platform. And in this paper, we have, as many of you maybe already know, the structure of the proton as a two-screening mechanism. The first screening creates a proton core black hole, which is a very specific feature of a four-dimension space-time. And then this proton core radiates through black body radiation with the Hawking temperature, the rest mass of the proton, which corresponded to a second screening. And tonight I want to focus on this very specific Hawking radiation, so that you can understand why gravity plays such an important role in the radiation of the mass energy of the proton. And this is the mass that we commonly interpret as the matter, the bionic matter. So this work was originally made by Hawking in the 70s with two very important papers, one in Nature called Black Hole Explosion, where he set up where he presented the initial calculations that he made. We won't go into much detail about the calculation, but I really want to give you the main physical argument to understand what is Hawking radiation and how black holes can emit particles. And this is why his second paper in 1975 was called Particle Creation by Black Holes, where he explained a little bit the consequences of his early calculation in 1974. And for the record, Hawking came up with these ideas after visiting several scientists in Russia, and especially a scientist called Zeldovich that we use also in our paper to explain how vacuum fluctuation, how an electromagnetic field can be transferred or is equivalently transferred to a gravitational field. And to understand what Hawking did in the 70s, so he combined two different theories that were doing their life independently, which is quantum field theory and general relativity. So quantum field theory is the science, the physics of quantum fields. So for example, the electromagnetic fields, here I just put the representation, the vector representation of electromagnetic field. Um, and it's generally made in a flat space-time, which is the Minkowski metric. So there is no variation. The space-time is assumed to be completely flat, which means no curvature. So if I sit somewhere in space-time, I won't feel any gravitational forces on me. And the specificity of the quantum field theory, why is it quantum? It's because the fields are not seen as vectors as in classical physics and as in the Maxwell equations, but they are seen in terms of operator. Here, I put a circle around the A and A dagger, and these correspond to the creation and annihilation operator, and they will play an important role in Hawking radiation, and I will explain you a little bit more what they describe and how do we use them. And it's very specific to the quantum field theory because those operators doesn't have direct physical meaning. They have been introduced by Dirac and Heisenberg. Heisenberg, when he was writing the matrix mechanics in the 20s, and they needed to integrate in the theory the fact that when they were observing the hydrogen spectral line, there were some relationships between the frequencies. So by summing the frequency, they could obtain another frequencies of the spectrum. And this very specific feature of the quantum scale could be integrated by using those operator, and the specificity of the quantization in quantum field theory is the fact that those operators cannot commute, such that when we multiply A and A dagger, it's not the same as A dagger A. And to obtain a real physical mechanism, for example, what is the electromagnetic field that I can measure and observe? Um, One need to calculate the mean value of those operators by using the quantum state. And in this presentation, we will study mainly the ground state, which correspond to the vacuum state, where no particles are present in the state. So Hawking combined this discipline with general relativity and maybe most of you know what generality is the work of Einstein's, who could express the gravitational force from a 4D space-time point of view using a Riemannian geometry. And Riemann in the late 19th century developed this geometry in curved spacetime. What does it mean to have a curved spacetime in 4 dimension with one temporal dimension and three um, um, space dimension? And so we generally represent the curvature as this, as if it was only a ball sitting, in a very elastic plate. But it's better to see it as a sink point where the fluid of space-time is flowing towards to. So it's better to visualize this like that. And why is it relevant in our paper? Why have we used those two concepts in the paper to describe the structure of the proton? Just to remind you, I put back this schematic of the proton structure, and each little dot corresponds to vacuum fluctuations. So those little electromagnetic energy density popping out of the vacuum that can be very erratic and with a mean value overall that can be zero, except if in very specific region of space where they can become coherent, which means that every neighbor have a relationship such that if an energy density pop up somewhere very next to it, another one can pop up as well. And when we study the collective behavior of those vacuum fluctuations, um, we can calculate the energy density. And the energy density is extremely high, such that generally in QFT, in quantum field theory, they are using flat spacetime. But when we deal with the vacuum fluctuations energy density or the zero-point energy, we can see that this energy density is extremely high, which means that in the Einstein field equation that relates an energy density to a curvature of spacetime that is interpreted as the gravitational force, we must integrate the fact that spacetime is curved at the proton scale and at the Planck scale. So this is why this very high energy density is curving spacetime. And we will see here how the curvature of spacetime will induce a radiation, and which is quite interesting. And we'll see how we can close the loop because vacuum fluctuation has been discovered by the blackbody radiation. And we'll see here how the curvature of spacetime can induce something that is very similar to the radiation of a blackbody. So that we can ask ourselves the question, is Hawking radiation an explanation of the blackbody radiation, or are any object something with an underlying black hole? And this is the thesis we are supporting at ISF. So as I told you earlier, it's easier to see the gravitational pull as a flow, flowing towards the center rather than just this bell shape of the curvature of a plate. So now let's dig a little bit more into what Hawking did. So his observation was that um, when I have a black hole somewhere in the universe, it's curving space-time. And at that time, they believed that the black hole were appearing because stars were collapsing. So the idea was if I have two observers, observer A, observer B, one observer very far from the collapsing star forming the black hole, and one observer very close to the star. So observer A has a ground state, has a metric system that is very flat because it's very far from the black hole. It doesn't feel anything. But as soon as the black hole is forming, then there is a time before the metric adjusts and so that you can feel that the black hole has been formed. But also there are some electromagnetic wave coming from an infinite path going towards the black hole. And as you may have seen before, when an electromagnetic wave goes towards a black hole, the, so the frequency of the wave, which is the temporal oscillation, will depend on how time is defined around the black hole and also in flat space-time. So the ground state that is observed by observer A on the flat space-time will then see its frequency to change. And we are talking about a blue shift because the wavelengths tends to be shortened because the time tends to be dilated. So this dilation induce a shift in the frequency spectrum. And the same way, the vacuum, the electromagnetic wave coming from the black hole towards the infinity will see a red shift, which means its wavelengths will be longer and the time will also contract. And by looking at the difference between the ground state, between the flat spacetime and the curved spacetime, he was able to calculate some radiation, and we will see how it works. But before understanding how it works, I would like to show you how the ground states in a region of space determine even the notion of particles. Um, so there are like a lot of information in this slide, but we'll take it slowly so that we can understand. So as I told you, in quantum field theory, any fields, any particles are determined by those operators, which are the creation and annihilation operators. And the definition of the annihilation operator is that when it acts on the ground state, it gives zero. So it annihilates, it's always the ground state gives zero. And the creation annihilator, when it acts on the ground state, it gives the quantum states written 1, which correspond to the existence of one particle. And this particle will depend on the field. For example, in our case, we are looking at the electromagnetic field, so the particle will be a photon. But we can also investigate the other field that will create other particles. And so I put this schematic to show you how a system can increase its number of particles. For example, if I've got a one state, I apply the creation operator, we'll have 2 particles, then 3, then n particles for undetermined number of particles. And I reduce the number of particles when I apply the annihilation operator. And as I told you earlier, the quantization rule is when I have the commutator of the creation annihilation operator, which is equal to 1. And we can also calculate the energy level of those states, which correspond to n plus 1/2 h bar omega. And for those who have followed former conferences, you remember that the vacuum fluctuations energy correspond to the 1/2 h bar omega, which correspond to the zero state when no particles are present in the system. So here, what is interesting is that, as I told you earlier in the former slide, function of the curvature, the direction of the time, or the how time is defined will vary, such that also the frequency that belongs to the ground state will vary, such that function of the gravitational field won't have the same ground state. So as if a gravitational field was creating like an atmosphere or an ambience, setting the ground state, and anything that I can observe according to quantum field theory is a difference with this ground state. So in quantum field theory, before taking into account the curvature of spacetime, and they were using a technique called renormalization because they obtained for the vacuum fluctuation a diverging energy density. This is what we address in the first part of the paper. And they needed to just remove those infinities and just to measure differences between infinities so that they could understand what is the physics of the system. But it was very unsatisfactory for many physicists like Dirac, who say that we are supposed not to discard infinities, we are supposed to discard very small quantities, which means that there is something in the ground state that can be very infinite that we just decided to forget because it was too hard to handle. And but it doesn't mean that it doesn't exist. So work here is to understand how we can use this very high ground state as as a source of energy. And this is why it's highly important to understand this. So if we go back to the Hawking radiation, to our little schematic, um, so as I told you, I have the vacuum fluctuation producing an electromagnetic field operator that we call E in or B in, like ingoing wave. So those are the waves who are living their life before the black hole appears. And they are traveling towards the black hole. And when they meet the black hole, there will be a different vacuum because of the curvature. And there will be a wave like going from the black hole that knows that there were curvature at the black hole, and then will go at infinity. And so the way Hawking wrote it is that the ground state at infinity and the ground state close to the black hole are different, such, such that we can write the creation annihilation operator at infinity like A and A dagger, and close to the black hole, B and B dagger. And what he calculated is how can I express B in terms of A and A dagger? Which means that the annihilation operator close to the black hole, which defines the ground state, because it gives zero. I should have put also here B of omega zero out is equal to zero. And I put an omega because you remember the energy of each operator is related to h bar omega. So this is why we have a little omega. And here, B omega is a linear relationship of A and A dagger. And if we now calculate, okay, what is the effect of this annihilation operator on the ground state far from the black hole, we can see that if beta omega is not non-zero, is different of zero, I will have the creation of a particle. Because we have A dagger applied to the ground state that will produce the one state. As a reminder, I'll go back here. You see, when I apply, when I look at creation, when I apply the creation to the ground state, I obtain one particle. So it's interesting to see that using this transformation due to the curvature, it could obtain the creation of a particle, and even calculated, okay, what is the probability of creating a particle? And so I put the result here. And what was quite astonishing is that it obtained the Planck spectrum here, 1 over exponential h bar omega over kt minus 1, which correspond to the Planck spectrum with the temperature that are written here, which is called now the Hawking temperature. And what we see here is that this temperature depends on the mass of the black hole, the large M here, the capital M, which means that the heavier the black hole, the lower the apparent temperature is. What it means also is that this black hole appear from a distant observer, this asymptotic observer A, as if the black hole was in equilibrium with a thermal bath of a temperature that depends on its mass, because it's very natural, because uh, I go backwards twice just to remind you that the radius of the black hole is related to its mass. So the size also, and the induced curvature, it corresponds also to the curvature of space-time, depends on its mass. So it just tells us that this temperature is related to the curvature of space-time. And later, I think it was 2 years later, another physicist called Unruh demonstrated that even in flat space-time, any accelerated object will see the surrounding vacuum as a thermal bath at a temperature dependent on its acceleration. So it's very interesting uh, how by just being accelerated, I will observe a temperature, and the more accelerate, the hotter the temperature will be. Um, so, and this acceleration in general relativity is called curvature. So it's a little bit the opposite as when you're on a motorcycle and you accelerate, and the more you accelerate, the colder you feel the air on your skin. But it's similar principle. So it strengthens also this idea that space-time is not pure vacuum. It's a kind of fluid that we call the Planck plasma in the paper. And another interesting fact is that this thermal bath at the Hawking temperature is following the Planck spectrum. So just to remind you, the Planck spectrum was the law that Max Planck discovered in 1901 to explain the black body radiation problem, which is which was okay, if I have an object at a temperature at a given temperature, what is the probability of emitting a photon at a certain wavelength? And it's interesting. So it was mainly dedicated to small object, quantum object, and this is also when he had to take into account the quantum nature of light and of those small oscillator that was constituting the matter. So it's interesting that with Hawking radiation, combining quantum field theory with curved space-time, he obtained similar results with the temperature, as if, as I told earlier, any black body would hide a curvature at its center, and this is what we showed in the paper. And maybe to finish, not to take too much time, this can explain also a relationship that we put at the end of the Hawking radiation in the paper. So I put it back here, where we can see that the energy of the proton is equal to the coherent vacuum fluctuation at the characteristic time of the proton, time its volume, and it's equal to the Hawking radiation of the internal core. And what it means is that the gravitational, so each PSU, each Planck scale unit that is produced by the vacuum fluctuation at the Planck scale, curving locally the space-time, when they are coherent on a much larger scale, such as the proton scale, they can create also a local curvature. And this curvature allows not only to maintain this coherency, this is what the first the first part of this equation is telling us about, but it also allows confinement and the radiation of the rest mass of the proton. So inside we have the coherent vacuum fluctuation that are producing the black hole that feed the Hawking radiation that then emit the rest mass of the proton. And in the paper, like I say, we also demonstrate that this gravitational field produced by the internal core also produce the strong force. I mean, what we call the strong force, which allows the different nuclei of an atom to be together and to form larger atom than the hydrogen that contain only one proton. And this is it for today for the Hawking radiation. It was a little bit dense, but I wanted also to explain you that in a later presentation, I will show you how in the end, flat space-time is not very stable, and that it's a very special case of that requires energy. For example, if you take something that is that is elastic, for example, a rod or a rope, um, if you don't stretch it, if you don't give energy, it will, curve naturally. And there are demonstrations of that also for space-time, as if naturally it evolved to what we can call a gas of wormhole as a natural state. So it's the counterbalance of the electromagnetic vacuum fluctuation. It's as if from a pure general relativity point of view, we can demonstrate that there are fluctuations of the metric that naturally emerge and that are associated to electromagnetic vacuum fluctuations. So it will be for another presentation, but it's just to give you an insight about how this relationship between curvature, electromagnetic field, and the concept of particle are intimately interconnected and related, and how also the curvature can contribute to the coherency in the Planck plasma. And that's it for today. So thank you for your attention. And now we will start to answer to your questions, if any. If there are any, oh, stop sharing. Okay. So don't hesitate to ask any question on the Q&A. It can be related to what we've just discussed, or it can also be related to any topic, and feel free to ask any question. I can see that in the chat there are already few questions. I'll try to go back. Every quantity that is close to zero has a very large reciprocal. Yeah, every non-infinite number has a reciprocal that's closer to zero. Yes, I think, John, you mean that, yeah, the inverse of any large number is very small, and in the holographic correspondence, we could observe that. It reminds me one of the calculation Nassim did in 2019 paper about the vacuum catastrophe, where he was able, and we take part of those results in this extending Action-Rosen vision paper, where he calculated what is the vacuum energy inside a sphere of the size of the proton, and he was able to recover uh, the energy of the universe, indicated that the information of all the objects can be found in the proton, that this relationship between very large and very small is it can be calculated. And the way I see it is that every bit information, the more information I have, every bit must be very small if the size doesn't grow, you know. can you talk about some of the first element if involved? Amaury, can you be more specific about your questions, or maybe I can ask you to join also. So yeah, feel free to ask questions, and maybe I can invite you, Amaury, to join. Mhm. Okay, Steven. Mhm. I will try to invite people. Attendees. Steven. So Steven, I will invite you to ask you your question.
Can you hear me? Ah,
Yes. Hello, Steven.
hi. Um, yeah, just to first to tell you, there was an issue with the audio. Whenever one of your animations was playing, it was very difficult to understand.
Ah,
But
okay.
getting back to the topic, and I must say I am a layperson, and I honestly couldn't really follow even with good audio because of the math involved. But that maybe
Ah, okay.
that's just me. I was just wondering because I recently saw a different talk that focused more on the photon as like the specific focus, of a grand theory. Can you
Hmm.
can you say how for you or for you guys proton seems to be more interesting than the photon as a specific focus?
Um, so um, the reason why we want to focus on the proton is this first is the fractal nature of the reality, uh, such that the if we understand properly the structure of the proton, we can better understand the structure of any scale.
Okay,
And this is why we are focusing on that. If we understand this elementary particle, we could then, by finding also scale relationship, understand, okay, what is the next scale after the proton? We have stars, and around stars we have planets, and the same way around the proton we have electrons. And how do we scale from the proton to larger scale? And but at the same time, the photon is interesting in the sense that it's the materialization of the electromagnetic field, and also the way we describe also the proton is an a self-gravitating electromagnetic field, which means that it's a photon highly energetic. It's a collection of photons that are highly energetic, such that they can curve space-time and be confined in the region of space that we call the proton, or the nucleus of an atom.
I see.
And so it's related. Uh, it has been called by Wheeler Geon. So Wheeler was studying, okay, what is an electromagnetic field that is self-confined, and what are those properties of these objects? And he wasn't able to connect these objects to particles because um, he didn't have like a proof, experimental proof for the vacuum fluctuations. And in our equations, it's the source term which allows the stability of those type of system. Because even for the Hawking radiation, yeah, it was a little bit technical, but I tried just to explain you what, because the ground state is the vacuum fluctuations energy, and I felt like it was important to understand that what the observable in quantum mechanics is above the ground state, but this ground state is a source of information of uh, the local geometry of
Okay, and
space-time, and this is why. this is why I wanted to focus on that today and to be maybe very specific about one point of the paper.
Okay.
And and this structure of the proton, that there is also another part of it is that for now we are just talking about the how mass is created, but there is also the charge of the proton that is very important to understand. And by looking at the dynamics of the Planck scale oscillator, we can also understand the emergence of charge, and we are currently working on that at the lab. And I hope we will be able to present you soon the result. And it's interesting because when we understand also how the charge emerged from the proton, we also understand how the electron is created around the proton.
Awesome. Thank you.
Yeah, you're welcome, Steven. So we have Coach Berry, um, Coach Berry, yeah, that ask a questions. I will ask him to join. Hello.
Can you hear me?
Yeah, I can hear you.
Hi. So I'm not a physicist, but I've had direct experience in inner levels about my comment there. So I was just interested in your comment on what I wrote.
Okay, my experience is that coherence is gravity, or at least there is not so much a cause and effect direction as a direct correlation, if not no difference between the two. Um, yes, yes. I mean, it's related to what we described. Yeah, what we described in the paper was the clear objective of that because um, some at the beginning we wanted to talk about how an electromagnetic field is converted into a gravitational field, but it's not a conversion because the two coexist. It's just different interpretation of the same underlying mechanism that we can either interpret in terms of electromagnetic field or in terms of gravity. And why I'm talking about this relationship, electromagnetism and gravity, because most of the time, coherency, we hear the coherency of light, of the photon of the electromagnetic field, and that is creating the gravitational field. So as soon as we remove coherency, we don't have gravitational field anymore because we need this coherency to create an energy density that is high enough to counterbalance the elasticity of space-time. And space-time is highly rigid. It's really hard to bend, so we need a very high energy density, and this is why it propagates very rapidly also. I don't
I
know if it's
appreciate that.
I don't know if it's
Yeah,
answer
I, I
your question.
appreciate that your response, and it's making me think some more. But I'm part of me just thinks that there's a lot to be gained by considering that coherence is the critical factor that's a kind of a much higher level of operation that
Mm,
can lead to other things. But of course, we have to look at activity, such as what you discussed, for understanding, giving us understanding about certain
mm.
processes.
Yeah, yeah. And I think the coherency, I mean, when you say that it can act at higher level, um, the way I will translate it into maybe experimental device or work is that this coherency can be produced in space without changing much the curvature of space-time. And so it can operate at certain frequency that can like propagate in space without curving too much space-time or yeah.
Yeah, and
I
that
don't know
and
if it's
that
clear.
and there's a
But,
relationship with that, direct relation to that with consciousness itself. Um,
mm,
Again, this isn't kind of the place to sort of get deeper into that right now, but yeah, that's again part of my some very powerful experience where
yeah.
consciousness has a much more overriding effect in
Mm,
all of this, to try to put it into words.
yes, yes, clearly. And this is why also maybe you've attended to the presentation of William last summer where he presented you the work he was doing with Nassim on consciousness and how even the notion of consciousness is related to to the structure of space-time itself, in which matter also emerge, and how even memory, even thoughts are thought to be like in the brain, but the brain are the cells, and the cells are made of molecules, are made of atoms, and the atoms are just specific feature of space-time itself that is connected then to coherency at higher level. So yes, clearly it's a very
Yeah, and
deep
it sounds a little
level of
bit it sounds a little bit nebulous when we start to have that part of the discussion, but it's interesting um, when we look at some of the science that's been done around consciousness and its kind of driving effect on actual physical processes. Um, yeah,
mm,
including anti-gravity around, physical objects, et cetera, et cetera. Anyway, I
mm.
didn't want to sort of detract it all from your talk, but I just couldn't help but sort of make a comment there. So thank you very much.
Okay. Yeah, thank you very much, Barry. So we have another question from Fabio. Um,
Hello, hello, Cyprien. How are you
Hello,
doing?
Fabio. Good, and you?
Very good too. Thank you very much. Congratulations for your presentation. I have this question, and maybe it's related to Barry's question as well, because when we talk about time and past and future, I tend to think as coherence, levels of coherence, where you say past have less coherence, and future you have more coherence, more complexity, more evolved. Let's put it this way. So I
Mm,
was wondering how would this what we call time, this illusion of time, emerges from all this in your opinion? If it's something
mm,
that's like static, that you have, you don't have time, you have coherence, coordinates, and less coherent coordinates that we call past and future that we move through it.
mm,
So how do you explain
mm.
this?
Yeah, it's hard questions. It's very interesting one. Um, it's just also in what you describe. Don't forget that there is also annihilation processes. Um, so we have more coherency, but some part of the system will also be annihilated, go back to the overall C before it
Mhm.
cohere again. So the question of time in this whole structure, I will say that it emerged as soon as a specific feature or a specific we describe vortices, but those vortices give also so as soon as there is a small curvature appearing, it gives a direction of time. It gives it gives an anchor on which we can hold to say, okay, time is going in that direction. And
Mhm.
and it's a very deep question, even from a pure theoretical point of view, because in general relativity, it's hard to determine the conservation of energy, which is related to this question of time. What is the flow? What is the direction of time? Because if I know the direction of time, um, in pure theory, they are calling them killing vectors. I can understand how the energy flow, how the energy is conserved. But as soon as the time is not well defined, for example, if I have a metric that evolves constantly, that has no proper uh, time directions, we cannot understand we cannot set this conservation of energy. And this is a very deep also problem in theoretical physics. And Einstein tried to solve this, and this is why he was very not satisfied by some part of the general relativity equations because he didn't have this energy conservation for
Mhm.
any metric system. Um, so s- there are also some people studying this question of time also for maybe you've heard the twin paradox. Uh,
Mhm. The
it's
paradox,
the
yeah.
story of two twins. One is going towards a black hole, and then the other one staying away. The fact that they do not experience the same time, will they age the same
Mhm.
way or not? And what happened to one or to the other? So uh, some people say that time is it's just very convenient to study trajectories, but it doesn't exist as you said. But to me, it's just as soon as we form a structure, a coherent region, we can then start to talk about time. But if if this coherency does not exist, yeah, we're like floating, and it's hard to determine in which way the system will evolve. Yeah. I don't know
Interesting.
if it's answer your question, but it gives you a few elements maybe to
Oh yeah,
think
yeah. No,
about.
I heard you. I think it's what you said is quite important to go deeper and understand. I have this question because you said the twin paradox. I remember that I think it's Andromeda paradox. Yeah, we here on Earth, if we could see some specific planet in the region of Andromeda, would
Mm,
be a specific time. We'd see, like for example, a rocket being built. And then in another coordinate, in another, I don't know, let's say another planet far from here, look at the same, at this, let's say the same present. You look at this planet in Andromeda, and this planet has already taken off. So it's gone. Because
mm,
although we are both in what we call present, since we are in different coordinates, we see Andromeda from a different perspective in
mm.
time.
Yeah, yes, clearly, because the behind those observations, there is the question of how we get the information. Can we get the information directly in real time as for example, now a Zoom call, we are different
Mhm.
point on the planet, but we can have like the same information almost instantaneously. But as soon as curvature is involved, um, we saw earlier in the presentation that when I have a more intense gravitational field, the time will tend to dilate. But
Mhm.
if the information go back, then it will contract again. So maybe we'll catch up the delay it had. So it's hard to
Mhm.
determine how the information how an observer that is very far get the information. Can we create shortcuts or not? Um, because most of the time people astronomers or people who are studying the stars can just perceive the light that arrives to us. So this is why we always say that they look in the past. And function of the distance, so people closer to Andromeda could see that the rocket has already taken off. So, but here we just see the rocket being built. Mm. And then the question is, well, yes, can we travel faster than this information traveling to us?
Perfect.
Can
Thank
we
you
have
very much.
shortcuts for that? Yeah, you're welcome, Fabio.
Thank you.
And then we have a question from Page. I hope I pronounce it well. Page 1.
Hello.
Yes.
Thank you.
Yes. Hello. 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 Hello.
Hello. Yeah, so I'm
Um,
just wondering
so
if you have a general layman's explanation for why we have quantum physics instead of just fluid or flow physics, and if that relates to the Riemann hypothesis.
just can you remind me what is the Riemann hypothesis?
Well, I'm not a mathematician, so I don't understand it very well, but it refers to the prime numbers and how they are
Okay, yeah. The hydrogen
Constrained.
energy level.
Yeah.
Okay. Okay. I will just mute you because I can hear myself while I'm responding, and then I unmute. Okay. Why are they quanta? Is comes from the very first quantum, which is what we describe as the Planck spherical unit, which correspond to this. So we talk about these vacuum fluctuations that we can observe experimentally. So when it's pure vacuum of matter, we can observe the vacuum fluctuations through, for example, the Casimir effect, or even by studying the electron orbits and their fluctuation of its orbit that can be measured. And also in the energy level of the hydrogen, we can also measure the effect of this vacuum. And when we study the energy of this vacuum in general relativity, we see that at that energy level, we form spherical entities at the Planck length. So this is why it's the cutoff we have been using, which means that above this frequency, or for smaller object, it's as if it was vibrating. The vibration was too high for the space-time to respond, When I have an elastic material, if I put a very high frequency, the rigidity or the viscosity of the fluid is strong enough so that it doesn't see the vibration is too rapid to accompany the oscillation. I can oscillate, and if the frequency goes too high, I don't see it anymore, and I just maintain a certain shape. So it explains why we have those spherical, creating a first discretization of space-time. So even though it's a fluid, we have geometric feature within this fluid appearing at the Planck scale. Is that part clear for you?
Yeah, I think so. So would that be related to the speed of light as a constraint in this particular universe?
Yeah. At least the speed of light is translating a property of the elasticity of space-time and how an electromagnetic field can be transferred from point one to point B. And the second reason for this quantization, the way I see it, is also the fact that everything is spinning and that the rotation is inducing a wavelength. The both the size and the speed of rotation gives a certain amount of energy and also set the path of oscillation or vibration that will be quantized. It's not like it's not a continuous possibility. So it's another explanation. And the and the third explanation is not probably down like many of them, is that when we observe the just the size of the object in the universe in terms of the universe, then we have um, supercluster of galaxies, cluster of galaxies, stars, um, atom or matter. We can see that they are precisely positioned in the on the scaling law, which which is similar to the acoustic wave in a resonant cavity. In a resonant cavity, we will see some specific point where we have nodes, and on specific nodes, we have like maximum of amplitude. And setting some resonance frequencies, creating those objects with different size. And this quantification is related to this resonance nature of the universe and how also all the protons and all the stars, all the galaxies, their size is well determined by where they are in the universe and this whole equilibrium between all objects. So sometimes the way I picture it myself is in terms of cosmogenesis. So the universe started with a one sphere popping out of another universe and then expand suddenly. And this expansion created a depression, and this depression must be counterbalanced by something, and those something are the 3D vortices that we describe as a toroidal flow, because by creating those features, because of this, the surface tension of space-time between the outside and the inside of the proton allows a pressure drop. So the depression of the decompression create those small particles that cannot appear anywhere, and they appear at very specific place in the universe with a very specific size. Is it clear enough?
Well, it's always more to ponder, but that definitely helps. Thank you so much.
Okay, you're welcome. Please. Um, okay, so if we don't have more questions, we can end the session tonight. I'm sorry for the animation, the correspondence between the my voice and animation that didn't work out. I will try to fix this for next time. I remember also the last time there were also some trouble. I will see if it's from Zoom or from my side. Thank you for being here tonight. It's always a great pleasure to have you, to respond to your questions. Very confronting, and it's so nice to see like so many people attending to the sessions. And yeah, please also send us your feedbacks. Some people say that it was too technical, and yeah, I'm sorry for that. I just wanted to pass few messages. So next time, I promise I will just put pictures, no equations. But this time it was hard to explain it without the equations. So I hope you enjoyed it. I wish you all a great evening or a great day for our friends from the US, Canada, Brazil. Thank you so much also for your comments. I really appreciate, and I see you very, very soon the next time. Bye bye, everyone.